Welcome to the mathematics session today. This is Temple AK Academy. Today we're looking at this very beautiful topic in mathematics known as surds. Surds, we have a lot of applications where numbers are expressed in surd forms. In trigonometry, we see a lot of angles having their trigonometric ratios expressed in surd form. So we need to have the understanding of surds. Very quickly, let's get into it. So there are other videos I've made like indices and logarithms. They go with this. So this is topic 6. Surds, let's get into it very quickly. A surd is a number that cannot be expressed in rational form, cannot be expressed as a rational number. What does that mean? We need to understand now what a rational number is. A rational number has the general form A divided by B, can be written as a fraction of this nature, where A and B are naturally occurring whole numbers, integers. So this is a rational number. Now, surds cannot be expressed in this form as a rational number. They cannot be accurately determined. They are roots that cannot be accurately determined. For example, square root of 2 cannot be determined as a recurring decimal. So we have square root of 2, it has the value 1.4142, and it continues. 13562, 13562. And it continues. If you put this in a calculator, you're going to get a chain of digits. So it cannot be accurately determined and expressed in the form A over B. Square root of 3 is another surd. This cannot be accurately determined. So we have this. If you put this in a calculator, you're going to get 1.7320508008, and it continues. So this cannot be accurately determined. Such a number that cannot be accurately determined, it has no end, is replaced by a simple number such as root 3. That is the advantage. That's the power of surds. We can express a chain of decimals that cannot be accurately determined in a simple form of that nature. So we have this as single surds, square root of 2 and square root of 3 as single surds. But we can have a combination of these surds, and they are also irrational. So if I combine square root of 2, either plus or minus square root of 3, this combination is also irrational and it's a surd. Even if I have a rational part, like 2, ordinary 2, minus square root of 3, for example, the presence of the root 3 in the combination marks the combination as irrational. So we're going to deal with this topic in this chapter. Let's move on into the next area. All right, now it's time to consider the laws of surds. So the manipulations here are based on special laws of surds. Let's get into these laws very quickly. The laws of surds, we have the first law. First law says the square root of a number can be broken down to give the product of the square roots of the factors of that number. Now, what this means is you have the product AB, for example. The law of surds says we can break this down into the product A multiplied by the square root of B. So each factor is represented, A right there with the surd square root on it, and B right there with the square root covering it. Okay, but in problem solving, we actually have to break this up in a special technique. So it is best to break the number into the greatest perfect square, the greatest or the largest perfect square, the greatest perfect square, and another number, the greatest perfect square and another number. So not just anyhow, but we break up into greatest perfect square, Yes, the greatest perfect square, of course, and another number, any other number, another number. That's how we break it up, another number. So the biggest perfect square we can find in number and another number. You know what perfect squares are? Numbers that are obtained by multiplying a figure by itself. So 1 squared, 1. 2 squared is 4. 3 squared is 9. 3 times 3. 3 multiplied by 3. 4 squared is 4 multiplied by 4. That is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64, and so on. And so on. So we're going to break our sorts to contain these perfect squares. Then we will be having a good chance of solving the problem. Let's have some examples. Supposing I have something like the square root of 32 occurring in a calculation. The best way to break this up is to find the biggest perfect square here. And can you guess? Can you make a quick guess? Of course, this will be broken into the square root of 16 and multiplied by the square root of 2. 16 times 2 gives 32. So this is the best way to break this up so that we can find the square root of 16 is actually plus or minus 4. Let's take the positive value 4 with the attachment of the square root of 2. So this is how we break this up. All right. So this is the first law of sorts. Let us consider the second law of sorts very quickly. The traces have to give way. The square root of a fraction is simplified by distributing the square root of the numerator and the denominator. We're going to distribute the square root to the numerator and the denominator. So we have a third of the form. We're going to distribute, okay, a third of the form, or square root of A divided by B. You can see this law says we'll give the square root of A, square root of A divided by the square root of B. So we can achieve this. Of course, in calculations, we're still going to continue with the process known as rationalization. We don't want this surd in the denominator. We have a technique to remove this surd from the denominator. We shall consider this in due course in the course of this lecture. Let us consider the third law. Okay, here we are. Let's take these traces away. Okay, now the product of the square root of the same number gives the number without the root. All right, you're looking at the product of root of the same number, square root of A, multiplied by the square root of the same number A. This will give A without the square root. This is the law. All right, and this can easily be proved. Yes, of course. The square root of A from indices. You have to find my video on indices. Very, very beautiful video, instructive. So this is A to the power half multiplied by the square root of A once again, which is A to the power half. And as you can see, the bases, that's what we call this, the bases are the same. So we continue the calculation by choosing the same base, since they are the same. And the combination law, we're multiplying, so we're going to add the powers. That means the first power, half, plus the second power, half. And this gives us half plus half in the powers. That is 1. And any number raised to the power 1 gives that same number. So square root of a number multiplied by square root of the same number gives that number without the square root. For example, if we have the square root of 2 multiplied by the square root of 2 in problem solving, we simply apply this law. Since we have the same figure in the square root, the answer is simply that figure, 2, without the square root. All right. So these are the main laws of sorts. Let us go ahead now and consider some illustrative calculations on how to apply these laws, specifically the algebra of sorts. In algebra of sorts, we are looking at the interaction between sorts, interactions between sorts, how sorts interact. And we're going to follow a series of laws that we have just studied. So these interactions can either be by addition and subtraction, addition or subtraction, multiplication and division. Let's get into it. Let's get into it. All right. So here we are, addition and subtraction to be considered first. All right. In order to add two surds of the form a root x plus or minus b root x. Notice here, notice that we can only add or subtract two surds provided their irrational parts are similar or the same. So you can see the square root of x in the left arm of the problem, the same square root of x in the right area. So we can combine them. And the pattern of the combination is taking the rational parts together after the order of the separating sign. So we're going to have, we take A, maintain the sign separating them, plus or minus as it is written, take the other one, B, and this arrangement will take along the irrational part, root x. This is it. So let us have an illustration here, an example. For example, if we have 5 root 2 plus 2 root 2. Of course, this can be added. The first thing to confirm is that the irrational parts are identical. Square root of 2, square root of 2. So allow the rational parts to interact after the order of the separating sign, which is plus. So 5 plus 2 gives us 7 with the attachment of the root 2 they both have. Very simple. Let's take a look at another one. 9 root 3, for example, minus 5 root 3. Let us look at this. How do we deal with this? Confirm, first, they have the same irrational part, root 3, which means they can be combined. And the combination is after the order of the rational parts. So 9 will interact with 5 after the order of this sign separating them. 9 minus 5 is actually 4, now with the attachment of root 3. You can form an analogy here. It's like making the root 3 to be the unknown. For example, you have something like 9x minus 5x. In algebra, you can easily fix this, of course. You can fix this. 9x minus 5x. 9 things minus 5 things. Those things are x. So 9 minus 5 straight away, and that gives you 4. And then with the attachment of the unknown x. So the same pattern. All right. Let us look at some illustrative examples on addition and subtraction. Let's go. Here we go. All right. Traces away. Okay. So let us look at the first one. All right. Now we have simplified the square root of 98 plus the square root of 32 minus the square root of 128. So the strategy is to split each of them according to our first law in this video. We're going to break 98 up into the biggest perfect square it contains and an order number. Okay, you can use the simple division pattern to get through that. Now we have 98. And now divide by the simplest number you can have. Let's divide by 2 and see. 2 goes, divides into 9, that's 4, remainder 1. That 1 placed by the side of the 8 to give 18. 2 divides into 18, and that's 9. Just look at that. Look at that. 49 is a perfect square. That's 7 squared. 49. So that's it. Mission completed. We can break 98 up into the biggest perfect square. So here we go. This is the square root of 49. That's right. Multiplied by the square root of 2. Now, as a general rule here, once we cite the surd square root of 2, it is an indication that we should attempt to break up the remaining surds to contain the square root of 2. Let's do that. For 32, of course, are you thinking about it already? For 32, if we divide by 2, 2 divides into 32 gives 16. And that is a perfect square once again. So we can maintain the sign plus and break up 32 into the square root of 16 multiplied by the square root of 2. Beautiful. Easy job. And in a similar manner, adopting the same pattern and suspecting that square root of 2 may be embedded in 128, we can confirm that by the same division pattern. Let's divide by 2 and see. Let's go. 2 divides into 12, 6. And 2 divides into 8, that's 4. Once again, here we are. 64 is a perfect square we like to retain. So this is sustain the sign, minus. Bring on square root of 64 multiplied by square root of 2. That's right. Now we have broken 98 up into square root of 49 and square root of 2. See that? And we have broken up square root of 32 into 16, square root of 16 and square root of 2. And finally, we have broken up square root of 128 into the square root of 64 and the square root of 2. Beautiful job. Now notice the occurrence of the square root of 2 in each arm of the problem. All right, let us evaluate each perfect square now. Next move, the square root of 49 straight away, 7, with the attachment of root 2, the irrational part. Move on, plus the square root of 16, evaluate that, that's 4, with the attachment of the square root of 2. And finally, the minus sign sustained, of course, the square root of 64, that's 8, with the attachment of the extra root 2. Beautiful. And at this point, we can already see the presence of root 2 in each of the terms, which means we allow their rational parts to interact. Let's go. Here we go. 7 plus 4, that gives us 11. The resulting 11 minus 8, that gives us 3. Now, with the attachment of that square root of 2, which is present in each of the terms, present in all the terms. And this is our final answer. As you can see, very simple. The high points, once again, breaking of each of the surds, square root of 98, 32, and 128 into the biggest perfect square they can have, and an ordinary number, which we realize that it is the same in each term. And now that inspires us to combine and get the final answer. Very, very simple. Come with me. Let us look at another example. Let's go. All right, here we are. Another example. Let us clear the traces. Now we have this 2 by square root of 18 plus 3 square root of 50 minus 4 square root of 72. Our target will be to break up these surds. Square root of 18, square root of 50, and square root of 72. Take a moment, pause the video. Can you already see the pattern that would result? Can you already see the biggest perfect square in 18? By dividing by a simple number like 2, you can easily see. 2 divides into 18, that's 9. 9 is a perfect square, so we bring a halt right there. This is going to be the already existing 2 with the square root of the biggest perfect square there is here, 9, and the remaining number, which is square root of 2. You can see square root of 9 times square root of 2, that's square root of 18. Now plus, let's go. We maintain 3. Break 50 up, you can see already, but let's show it here. Let's show it. 2 can divide into 50. 2 divide into 5, that's 2. Remainder 1. 1 by the side of the 0, that's a 10. 2 divides into 10 gives us 5. And of course, a perfect square. So square root of 50 can be broken into the square root of 25 and the square root of 2. We continue. The minus sign sustained. 4 retained. And now we get ready to break up this 72. So let's break up. You can see already 2 divides into 72. 2 divides into 7 gives us 3. There's a remainder 1. 1 by the side of the 2, making 12. 2 divides into 12 gives us 6. Wonderful. Another perfect square. Can you see that? So we can break 72 into the square root of 36 multiplied by the square root of 2. 36 times 2 gives us 72. All right. Next stage, evaluation of each of the perfect squares. Let's go. 2. So let's take it easy. Don't rush it. 2 will multiply the square root of 9, which is 3. Now to multiply the existing root 2. So we have dealt with the first area. Yes, square root of 9, the change. Square root of 9 give us 3. Now the sign separating them, maintained plus maintain the sign. 3 sustained multiplied by the square root of 25, and that's 5, with the attachment of the square root of 2. And in the last term, we have the minus sustained, 4 written, the existing 4, of course. Now the square root of 36, that is multiplied by 6, which is the square root of 36 here, and then times multiplied by the square root of 2. That's right. Now let us combine the rational parts. 2 will have to be multiplied by 3, get the result. 3 will multiply by 5, get the result there, and 4 multiplied by 6. Let's go on. So this will give us 2 times 3, that's 6, with root 2 attached, of course, plus 3 times 5, that gives us 15, with root 2 attached, and minus 4 times 6, so that's the minus sustained there. 4 times 6, that's 24, with root 2 attached. Now let's do the evaluation very quickly. All of them, each of the terms contains the square root of 2, which means they can be combined. Let's go with the combination. The rational parts will take the lead. 6 plus 15, that gives us 21. The 21 now, minus 24. 21 minus 24, that's minus 3, and now with the attachment of the root 2, which all of them have, our final answer. Very simple. Yes, very simple, you can see. So the high points again, breaking each of the surds, square root of 18, square root of 50, and square root of 72 by way of division into the biggest perfect square and ordinary number, observing that the square root of 2 occurs in each of the terms, elicited the combination, and we have the final answer. Let us take one more example. This video is not an entertaining video. It's a full, complete analysis of the topic logarithm. And you see, my videos are designed to give you full knowledge of the topic. You study my videos, is paid to that topic. Anywhere you encounter the topic, you are a problem solver. You move from learner into being a master. Come with me, let us look at the next one, right? Of course, the traces have to go away. Another one, let's go. Square root of 12 plus square root of 27 minus square root of 75. Let's go. So the breakage, can you figure, we should be faster now. You can see the perfect square already, 4 times 3 already. Now, move on to master level. You don't need to start doing the division. You can figure it out. So square root of 4 multiplied by the square root of 3, because 4 times 3 gives us 12. So we have just done justice to that. Go for the square root of 27 in a similar manner. What are you thinking of? Sustain the plus, of course. Yes. And what are you thinking of? 27. You want to divide by another number, which is not 2. 2 cannot divide into 27. 27 is an odd number. So let's go for the next number, which is 3. Clearly, you can see 3 divides into 27, of course. 9. Here we go. A perfect square. So 9 multiplied by 3 generates 27. Let's break it up. Square root of 9 multiplied by square root of 3 gives us 27. And the minus sign sustained. Break up 75. Let's go. You can figure it out already. Okay, let's do the formality here. 75. Allow 3 to divide, of course, because this is odd. 3 divides into 75. Take it gently, digit by digit. 3 divides into 7, that's 2. 6, which gives remainder 1. Remainder 1 by the side of 5, 15. 3 divides into 15, 5. So we have a perfect square, 25. 25 multiplies 3 to give 75. So the breakage is clear. The square root of 25 multiplied by the square root of 3. Now the next line, evaluation of each perfect square. Each perfect square, the root of each of the perfect squares, evaluate. Let's go. Square root of 4, and that is 2, with the attachment of root 3, plus square root of 9, and that is 3, with the attachment of root 3, and minus the last area, square root of 25 is 5, of course, with the attachment of root 3. What do you notice here? What do you observe? The square root of 3 present in each of the terms. That inspires us to combine them. Let's combine them after the order of their separating signs. So 2 plus 3 gives you 5, and 5 minus 5, that gives us 0. 0 with the attachment of root 3. 0 as coefficient by the side of any sort renders everything as 0. Our final answer. Very simple. Okay, so much for addition and subtraction. So let's take a step further. Now we're into multiplication. Beautiful. To multiply surds, we simply follow a general rule. We multiply surds, multiply every component of the surd. What do I mean by that? Let us consider minus a root x to multiply positive b root y. Let's consider this. We multiply all components. Of course, the sign of this b root y here is plus, even though it is not written. By convention, we don't write the plus sign there. It is implied, it is present. Now we multiply every component, sign for sign. So plus times minus gives us the minus, prevailing sign. Rational part for rational part, which is a times b, gives us ab. Then irrational part for irrational part. The square root of x multiplied by square root of y, a reversal of the first law we studied in this video. So we're going to recombine as x multiplied by y. Remember, the law is reversible. So if we have the square root of xy, the law of surds says this can be broken up into the square root of x multiplied by the square root of y. A recombination is also possible. So we can recombine square root of x multiplied by square root of y as a single unit, the square root, common root of the products of x and y. So this is reversible, and that is what we have here. Once again, sign must multiply sign, rational part for rational part, and then irrational part, the surd, for the irrational part, the surd. Let us move on with examples to illustrate this pattern. Come with me. We're looking at examples right away. Yes, here we go. Here we go. Let us take these traces away. And of course, I should have a better color of marker. I should have a better color of marker. Yes, let's go. Let's go now. To inspect, the surds are different here. You can see. So this is multiplication. Let's go. Sign for sign. The sign here is positive, as you observe, not written. The sign here is positive. So our answer begins with a positive sign, of course. Now, rational part for rational part. 3 multiplied by 4. 3 times 4, we have 12. And now the irrational part, the surds, we go together. Square root of 2 times square root of 5. And that is square roots combined. The product, 2 multiplied by 5, gives us 10. Our final answer. It's as simple as that. Very simple, yes. Of course. Let us take on the next example to watch our learning. All right. Okay. Let's give away the traces. Now we have the next example. 2 root 3 multiplied by 3 root 2 multiplied by 4 root 5. Here we are. So let us take the signs, plus multiplied by plus, multiplied by plus. Our answer is going to begin with a positive sign. Now, the real parts, or the rational parts rather. Let's go. 2 has to multiply 3. That gives us 6. 6 has to multiply 4. 6 times 4, and that's 24. Now, let us multiply the surds. All of them are different. Square root of 3, square root of 2, and square root of 5. Let's take them together. 3 times 2, 6. 6 multiplied by 5, 30. So we have a common square root of 30. So this is very easy to handle, very simple. So that's the pattern with multiplication. What if you have something like minus 3 root 2 multiplying 4 root 3? How about this? What do we do? Sign for sign. Let's go. The sign of this second term here is a plus, although not show. So sign for sign, let's go. Minus times plus, we're going to have minus. Negative sign prevails. The rational part for the rational part. 3 multiplies 4. 3 times 4, we're going to get 12. That's right. And now the surd for surd. Root 2 times root 3 must give us root 6. So it's the same approach. Very simple. Sine for sine, rational part for rational part, surd, irrational part for surd, irrational part. Let's move on with our learning. It's getting exciting, of course. Now, let's do something very important. Let us take these 2 steps. If you like this video, you enjoy the studies, it's a very, very beautiful channel. You have a lot of wonderful videos here. So please subscribe to this channel now if you have not done that. And turn on this notification bell. Very important. This bell will alert you anytime I make videos. You go on, you have the alert, you go on and learn. Please subscribe, turn on this notification bell now. Thank you. Let's move on. Let's move on. Okay, now we consider division. Division of surds. Division of surds. Let's go. So division of surds is done by a special process known as rationalization. So we want to say rationalization is the rule. Rationalization, of course. This is the rule. Rationalization. All right. Rationalization. This is simply a process that removes the surd from the denominator. So it involves the removal of the surd. So you can see, making it rational, from being irrational to rational. So this involves the removal. Let me tidy this up and write something better. The removal of the surd. Removal of the surd, that's the square root expression, from the denominator. The denominator is the target here. We're removing the surd from the denominator. How do we do that? We do that by multiplying both the numerator and the denominator by a factor usually taken from the denominator, such that the surd will be completely removed from the denominator. That is it. So let us get into it. Please come with me. Let's get into it. Now, here we are. Let us take these traces away. The denominator in this case, case 1, the denominator involves a single surd. Now we have a surd of the form square root of a being divided by another one, square root of b, in this form. This is the form. Rationalization here involves the use of the surd in the bottom to multiply both the numerator and denominator. So we're going to say this surd, square root of b, go ahead and multiply the numerator with b, and go ahead and multiply the denominator with b. As you can see, there is no change. No change, absolutely no change is made here, because now we can divide both of them. You can see we can divide, strike out square root of b from both the numerator and denominator and still obtain the original expression. But that's not the aim. That's not what we're going to do. We're going to have to combine numerator for numerator, denominator for denominator, so that we can get the surd out of the denominator. There we are. Let's go. Square root of a multiplied by square root of b, the combination, of course, the law 1 in this video, ab, the reverse of the law 1. Now, divided by, now, here we are, our law 3, square root of the same surd. Can you see? The same surd multiplied by the same surd is going to give us b, the number without the surd. Observe this pattern. Beautiful. Now, let us go straight into illustrative examples to see how this is done. You can see at the end of the day, we have an expression without the surd in the bottom. The surd is not in the bottom anymore. The expression has transitioned from being irrational to being rational. So we have made that which was irrational to become rational, rationalization. Come with me. We have to consider some examples right now. Let's go straight away. Get the traces out of the way. And of course, square root of root 3, square root of 3 in the bottom, as you can see, square root of 3 in the bottom. So we have to do justice to that. And that is what we decide what we use in the numerator and denominator. Let's go. So this is straight away. Use the square root of 3 for the numerator. 6 multiplies square root of 3 in the numerator divided by the same Root 3 multiplies itself in the denominator. That is it. Let us combine them now. Do not cancel. We're not in for that. Let's go. 6 multiplies root 3, 6 root 3. Divided by root 3 times root 3, and that gives us ordinary 3 without the roots, according to law. And now you can check through. The 3 can divide, not through this, of course. The 3 here is shielded by the square root sign, so you can't do that. Let's go. 3 divides into 6, we have 2. And the final answer comes up 2 root 3. No surd in the denominator. Very simple. Let us go through learning. The second example is available to do that for us. Let's go. Here we are. Get the traces out of the way. Yes. Here we are. 5 divided by 2 root 3. We want to get this root 3 out of the way. Now, the idea here, make it easy. Don't take the 2, which is a rational number, along. That makes it easy. So we can simply take only the surd. Only the surd suffices. Let's go. 5 multiplied by root 3 in the numerator, divided by the original denominator, which is 2 root 3. Now, don't take the 2 along, times another root 3. So only the surd. You can see root 3 in the numerator, another root 3. But now let us multiply out. 5 multiplied by root 3, and that gives us 5 root 3. All right, divided by, let's go. How do we multiply this? 2 prevails there. Let's seize it. Multiply by the result of root 3 multiplied by root 3. Root 3 times root 3 is ordinary 3. And now we combine this. So we have 2 times 3 gives 6 on that. Once again, separate out the 2. That is it. And then get the result of root 3 times root 3, which is 3. And 2 multiplied by 3 gives us 6. That's right. Very simple. Final answer there. Let's move on. And the final example in this particular session, let's see. That's right. And get the traces out of the way for space. Good. Now we have root 5 divided by 3 with root 2. Once again, do not take the rational part, which is this 3, along. So let us have it. This is going to be root 5 in the numerator multiplied by the surd. Just use the surd. The surd is root 2, square root of 2, divided by the denominator, which is 3 root 2, also multiplied by the surd, root 2. And you know the pattern from the previous example. Let's combine this by multiplying. Let's go. Root 5 times root 2, that is root 10. Root 10 divided by, let's go, separate out the 3 and wait for the arrival of the result of root 2 times root 2. Root 2 times root 2, same number, right? The surd gives way. You know that by law. So now we can go 3 times 2 gives us 6, our final answer. No surd in the denominator. And that is it. Okay, we move on. Let's match on. Let's match on. Now we have the denominator involving a binary surd, which means there are 2 components in the denominator. All right. So this follows a special pattern. And now we have to introduce the concept of conjugate surds. Conjugation is the rule here. Conjugate surds. Conjugate surds. Conjugate surds are associated with binary surds, of course. So you have to have 2 parts in the surd. If you have a surd, the square root of A, let me say plus the square root of B. This is a binary surd. It has 2 parts. The first one on the left-hand side, the second one on the right-hand side, separated by the sign in between them. Translate this by conjugation. The conjugate of this is simply retain the same surds. Retain the same surds. Square root of A and square root of B. But the only thing that you change will be the sign in between them. Originally plus, translate into minus. So the conjugate of square root of A plus square root of B is another surd, square root of A minus square root of B. Let's take another one. Supposing you have a rational part in it, of course, combining with the irrational part, rendering the whole arrangement as irrational. Square root of 2 plus square root of 3. we can have the conjugate of this. The conjugate will be retain the original values the way they are. So retain 2 and retain square root of 3. Only change the sign in between them. Plus translates into minus. So as a generalization here, we can say if we have square root of x, either plus or minus the square root of y, the conjugate of this will simply be retention of the square root of x and that square root of y, but with a reversal of the sign separating them. So where we have plus, we must have minus. And where we have minus, it must become plus. So plus or minus becomes minus or plus. Now, this conjugate will be used to multiply both the numerator and the denominator to get the sort out of the denominator and giving us an expression that is rational. Now, come with me. Let us take a look at some examples to see how it works. All right. So we have an example. Let's take this 360 way and choose that color of marker. That way. Okay, let's go. Come with me. Let's go. This is 1 plus root 3 plus root 2. And now think of the conjugate of this denominator. Can you figure it out? What is the conjugate of root 3 plus root 2? Of course, root 3, right? Conjugate is root 3, of course, minus root 2. This is the conjugate, root 3 minus root 2. And now we're going to use this to multiply both the numerator and denominator. And now we write straight away. 1 multiplies this conjugate to give the same thing. 1 has to multiply this conjugate. So we have square root of 3 minus square root of 2 in the numerator. All of this divided by, we have originally. So here comes our bracket, square root of 3 plus square root of 2, originally present, multiplied by the conjugate that we have. So square root of 3 minus square root of 2. Take a moment. Verify that we have not altered anything in this resulting expression. Verify it. Of course, as you can see, the square root of 3 minus square root of 2 can strike out completely the square root of 3 minus the square root of 2, giving back the original expression. But we're not interested in this cancellation. We want to do this expansion. Now, here comes our rule in algebra. Take a look at the brackets in the bottom. The same arms, square root of 3 and square root of 2. The same thing, square root of 3 minus square root of 2. This shows us a difference of two squares. We have the expression a plus b in one bracket or parenthesis, and then you have the same thing, a minus b in the second. You have to get my video in algebra where I dealt with algebraic simplifications and factorizations. Here, difference of two squares. You simply take the first and square. Difference means subtraction. And take the last one and also square. Mission completed. You don't need to go through the expansion process. Yes, this is a difference. And this is a recurring pattern when it comes to conjugate sort. So you can use this pattern and you are correct. This is not a shortcut. It's application of a principle. So let's go. This becomes square root of 3 minus square root of 2 divided by, this is a difference of two squares. So take the first one totally, square root of 3, maintain a square on it, and go ahead, subtract. Take the last one, square root of 2 also, and maintain a square on it. Can you already see clearly? Can you see what can happen here? So this is going to give us, if we continue on this side, it will be square root of 3 minus square root of 2 divided by, now evaluate each of these squares. Root 3 squared, that's a way of saying root 3 multiplied by root 3 a second time. Root 3 squared means duplicating root 3 times root 3. And you can see this is already 3. So it's a way of saying the square takes off the root. The square takes off the root. You have the prevailing 3 right there. Retain the sign between them, the minus. That's it. And now do the same thing. The square removes the root. So we have ordinary 2. And now the finishing. Finish it off. Root 3 minus root 2 divided by, take the difference, 3 minus 2, and that's 1. And now you know any expression divided by 1 gives the same expression. Final answer, root 3 minus root 2. Very simple. Very simple. The high points once again, when it comes to a binary surd in the denominator, we have to find the conjugate of that binary surd. Use the conjugate of the binary surd to multiply the numerator and the denominator. Observe a general trend. The denominator is the expansion of a difference of two squares, and make the work flow in that manner. All right. Let us take on another example to buttress our learning. You can see this video is full of examples. Mastery and expertise are product of persistence and consistency in practice. You have to use a lot of examples. Repetition guarantees cognition. So if you want to recognize patterns, you have to solve examples repeatedly. And that's what this video is doing for you. So come with me. Let us take a look. Another one. Here we have it. Another one. Take the traces off. Okay. And now, let's go. Square root of 3 plus 1 in the numerator divided by square root of 3 minus 1 in the denominator. Let's go for it. So here we have, it is going to be settle the conjugate of the denominator. What is the conjugate of this denominator? Can you figure it out? Pause the video, figure it out. The same writings, square root of 3 and 1. These are the participating figures. Square root of 3 and 1. Now change the sign from minus to plus. This is the conjugate of the denominator. This will be used to multiply both the numerator and the denominator. Let's go for it. So this is going to give us the square root of 3 plus 1 multiplied by another round of square root of 3 plus 1. You can see, so a duplication actually. We have the first one from this numerator, square root of 3 plus 1, that is this, and our conjugate of the denominator, and that is this. All right. Divided by, let's go, the usual pattern in the denominator. It's going to be a difference of two squares. It's a regular pattern. So we have the square root of 3 minus 1 already existing. That is the denominator. Yes, this one. Into the conjugate that we developed, which is square root of 3 plus 1. That's right. Now, expansion of the numerator. I'm going to show you a pattern up here. I'm going to show you this pattern, but let's do the expansion. Let's do the expansion of brackets. Let's go. Square root of 3. We have to multiply each of these terms in the numerator here. Square root of 3, the first term, multiplies every term in the bracket. Let's go. Square root of 3 times square root of 3, of course. 3, you can answer that easily. Now, square root of 3 times 1, positive square root of 3. Now it is the turn of 1 to expand the bracket. Let's go. 1 times square root of 3, positive square root of 3, because the 1 is positive, and so is the square root of 3. Finally, 1 times 1, positive 1. And now, don't forget your regular pattern in the denominator. The same terms, square root of 3 and 1, square root of 3 and 1, in two different brackets. The only difference is a minus in the first, a plus in the second. Therefore, it's a difference of two squares. Square root of 3, maintain the perfect square, minus the second term, 1, and maintain your perfect square. Beautiful. Now combine like terms in the numerator. Let's go. The rational parts must go together. 3 doesn't have a surd, doesn't have a square root, and 1 doesn't have, so they are like terms. Let's take them together. 3 plus 1, that gives us 4. And now let's take the surds together, the irrational parts. Let's take them together. Plus root 3 plus root 3. You can figure this out as 1 root 3 plus 1 more root 3, making 2 root 3. It's like having x plus x. You know, you have 2x. All right. Now evaluate each of these perfect squares. Let's go. Square root of 3 squared. We've learned that the square will remove the root. So you have 3 prevailing minus 1 squared. 1 times 1 is still 1. Let's continue the onslaught around here. Now we have 4 plus 2 root 3 divided by 3 minus 1, and that is 2. Beautiful. How do we get past this? Citing 2 can divide into the 2 arms. So we decide to distribute the denominator to each of the components in the numerator. Let's go. Do that. 4 receive divided by 2 plus, let's go, 2 root 3 also receive divided by 2. We can distribute, of course, 2 to each of the terms in the numerator. That's what we've done. And now you can divide very quickly. 2 divides into 4, gives us 2 right there. And then 2 divides into 2 without. So we can have the final answer, which is 2 plus root 3 as our final answer. Very simple. Very simple. Now, if you have studied my video in algebra, you know that I discussed perfect square forms. Take a look at what I said I was coming back to discuss. Yes, now I'm back to it. Square root of 3 plus 1 in one bracket. The same square root of 3 plus 1 in the second bracket. This is a duplication, which means we can represent as the square root of 3 plus 1 raised to the power 2. It's a duplication. X times x is x squared. So the same expression multiplied by itself means that expression squared. And now we can use the perfect square form. What is this perfect square form? Squared, it is a pattern. It is a pattern. And let me show the pattern here. So supposing you have a plus b, and you like to square this, take the first one and square. A squared, retain the sign separating them. It is a plus here. So plus, retained. Now multiply everything you see. 2 times a times b, 2ab. Multiply everything you see. That's everything you see here. 2ab. 2ab will be in the middle. And the last one is always positive, no matter the separating sign around here. Last one here is always positive. And now take the last one and square it after the order of the first one. We square the first one. So this is the pattern here. Let's apply it. We're going to have this as the square root of 3. Give it a square. Now maintain the sign separating them, which is plus. Multiply everything you see. 2 times 1, 2 times root 3, 2 root 3. This is a perfect square form. Plus, square the last one. 1 squared, 1. Then evaluate this. So you have the square will remove the root. You have ordinary 3 plus 2 root 3 in the middle. That's this term. And finally, plus the extra 1 over there. And now you can take the rational parts together. 3 plus 1. Now, 4 plus 2 root 3. Beautiful. It comes to the same term we obtained. 4 plus 2 root 3, the same way we obtained it here. 4 plus 2 root 3. So learn the perfect square form. Study my video in algebra, algebraic simplification and factorization. So you have to look for that video in my channel, on my channel, and then study. Let's go into the next example. Let's go come with me. Beautiful. And now this is an involved example. Let's clear the traces away. This is an involved example. Let's go. Why is it involved? You have some figures by the side of the square root of 3 here. You have 2 by the side, so more involved. Let's go. Determine very quickly the conjugate of the denominator. What's the conjugate of the denominator? Let's go. And it's going to be the same terms, 2 root 3 and root 2. But now separated by a different sign, opposite their original sign. Plus here originally, now we have minus. This is the conjugate we're going to use to multiply the numerator and the denominator. So let's go. And this is going to be, take the numerator in bracket. It is binary. There are 2 terms. So take it in the bracket, 2 root 3, to avoid mistakes, minus root 2 into the second, which is the conjugate of the denominator. Let's go. 2 root 3 minus root 2. That's right. Now divided by, we already know it's going to result in difference of 2 squares. You can write that. But now, if you want us to be gentle, of course, and why not? This is 2 root 3 plus root 2 into the conjugate, which is 2 root 3 minus root 2. That's right. And now let's do the normal expansion for the numerator, which is a perfect square form actually, but let's do the normal expansion. This is 2 root 3 multiplied by 2 root 3. So out here, 2 root 3 multiplied by 2 root 3. So let's multiply. We discussed this in multiplication earlier in this video. The rational parts go together. 2 times 2 gives us 4. Now the surds go together. Root 3 times root 3, that's 3 without the root. And 4 multiplied by 3 generates 12. So our first result is 12 there. Now allow 2 root 3 to multiply the root 2. So you can see that here, 2 root 3 sets out to multiply root 2. So real part, 2 multiplied by 1 there, that's 2. Then the surd, root 3 times root 2, definitely root 6. So we have, and you can see there is a minus sign there. Did you notice the minus sign? There is a minus sign around there, so a minus sign prevails. We have 2 root 3 multiplied by the negative root 2. So that's going to be negative 2 root 6. It is easy to understand that from here. 2 root 3 multiplied by negative root 2. Positive sign here times minus, prevalent sign minus. The rational part, 2 times 1, 2 prevails. Then the irrational part with the root, root 3 times root 2, and that is root 6. So we have this term here. Beautiful. Now it is the turn of negative root 2 to expand the bracket. Negative root 2, we have negative root 2, we have to deal with this first. Negative root 2 times 2 root 3. Negative root 2 multiplied by 2 root 3. How do we go? Sign for sign, minus times the plus here, which is minus. And then the prevalent rational form of it is 2, the part of it. Then the surd can go together. Root 2 times root 3, which gives us root 6. So we have negative 2 with root 6 attached. And finally, negative root 2 will multiply negative root 2. So we have this form, negative root 2 times negative root 2. Sign for sign very quickly. Minus times minus, that gives us plus. Surd for surd, root 2 times root 2, that gives us 2. So we have positive 2. And don't reconsider, the bottom is a difference of 2 squares. So you can see 2 root 3, 2 root 3, the same terms, root 2 and root 2. The difference is in their sign. Plus in the first bracket, minus in the second bracket, the pattern of the difference of 2 squares. Very quickly, 2 root 3, all of that squared. The minus root 2, also squared. So let's do the combination in the numerator. In the numerator, let us take like terms together. The parts that are rational without the square root expressions. Let's take them together. 12 plus 2 gives us 14. The minus 2 root 2 minus 2 root 6 minus 2 root 6 is like having to deal with minus 2x minus 2x, where x is the unknown. You know, this is minus 4x. So the root 6 behave the same way like the variable there. All right. Minus 2 root 6 minus 2 root 6 minus 4 with the attachment of the root 6. That's the numerator. Now evaluate these perfect square forms in the denominator. How do we do that? 2 root 3 to be squared. So let us clear some space. Yes, I have to do some erase so that we have space here. It's exciting, very beautiful. Difference of 2 squares in the bottom. So it's about rapid pattern recognition. You have to recognize patterns rapidly. This is what we do. Once we get to this point, you apply it. Rapid pattern recognition. All right. So let's go. And this is going to give us, let's see, how do we square 2 root 3? 2 root 3 squared means 2 root 3 multiplying itself. 2 root 3. So let's evaluate this. Now, they are both positive, so our result is going to be positive. Now the rational parts go together. 2 multiplied by 2 gives us 4. Multiplied by root 3 times root 3, the 3 without the root, according to law. Now 4 times 3 generates 12. So we have 12 as our first result here. Then minus root 2 square. We've been through this. The square simply removes the root, so we have ordinary 2. Now evaluate the bottom. Evaluate the bottom. So you have 14 minus 4 root 6 divided by 12 minus 2, which gives us 10. And now we can't divide outrightly by 10, so we have to distribute. Let's do a factorization instead. Let us factorize the numerator. 2 can divide into 14. 2 can divide into 4. So let's factorize 2. Factor 2 out. 2 divides into 14. We have 7. Minus 2 divides into 4. We have 2 with the attachment of the root 6. All of this divided by 10. And now we can divide. 2 divides into 10, gives us 5. Our final answer will take the form 7, no need for the bracket anymore, minus 2 root 6, all divided by 5. Our final answer. Very simple. Very simple, isn't it? Very, very simple. There can be another form of this expression. We can decide to write, or a second form of the answer, we can decide to write 1 over 5 into 7 minus 2 root 6. This is another form for multiple choice type of questions where the option can be arranged in different formats. And therefore, you have to tailor your answer to the format of the options provided by the examiner. So this is another form of writing this, the final answer. All right, let's proceed. Let's move on. All right. And the traces we have to go. Okay. All right. Now we have P is given to us as 2 plus root 3. And we have to find P minus 1 over P. All right, so let's get into it. Substitution is the rule. Anywhere we have P in the problem to be solved, we simply introduce or substitute 2 plus root 3. Let's get into it. So P minus 1 over P straight away. P minus 1 over P straight away by substitution. Replacing P with the given expression is going to be 2 plus root 3 minus. And now, very important, once you have a minus interacting with a binary expression, an expression containing more than one term, the bracket is necessary. Without the bracket, we could be wrong. So the bracket is good security around here. Minus 1 over 2 plus root 3. So one thing you've learned from this video is that this bracket must be put in place here. Go ahead and write the minus without the bracket. It could increase the chances of being wrong. All right. So this is going to be 2 plus root 3 minus, and that is the pressure area. So leave the minus, don't operate with it. Let us evaluate the pressure area. The conjugate of the bottom, of course, will be used here. The conjugate of this denominator is actually 2 minus root 3. You know why and you know how. The same 2 and the same root 3, original plus between them translates into minus. And we're going to use this for the numerator, multiply the denominator. So 1 times this expression is the same as 2 minus root 3. Divided by, the bottom is, of course, the original 2 plus root 3 to be multiplied by its conjugate, which is 2 minus root 3, generating the factors of a difference of 2 squares. Can you see that? So let us go ahead. This is going to give us 2 plus root 3. Now minus 2 minus root 3 divided by, let us go ahead, difference of 2 squares. So take the first one, which is 2 squared, minus is a difference. So minus. Take the second one, it is root 3, and maintain its square. Beautiful. Let's go on. And this is going to give us, we already have 2 plus root 3. Minus sign sustained, bracket retained. And now we have 2 minus root 3. Evaluate the denominators. Let's go. 2 squared straight away, 4. Minus root 3 squared also, ordinary 3. That's right. And now let's continue in this area. This is going to give us 2 plus root 3 minus do the final evaluation. 2 minus root 3 divided by the result of the interaction here. 4 minus 3 straight away is 1. And any expression divided by 1 gives that same expression. So patiently, we still have 2 plus root 3 minus the whole of divide by 1, the same expression. So we have 2 minus root 3. Now, the decisive moment. That moment when the minus sign opens up the bracket by expansion. Let's go. So you have 2 plus root 3. The minus has to do that job. Minus multiplies the first one. Minus times 2, minus 2. Minus multiplies the second one. Minus times minus a plus. And we have root 3. And now the finishing, the final knockout. The final knockout, let's go. 2 minus 2, the rational parts interact. 2 minus 2 gives us a 0. Same term eliminates. 2 minus 2 gives us a 0. Then root 3 plus root 3 gives us 2 root 3. Our final answer. Very simple. The high point here, you have operations with a binary sort. The bracket is the deciding factor here. Decides whether we're correct or we'll be wrong. All right. So let's move on. Beautiful. All right. Okay. So now you have to solve, like I stated earlier in this video, you have to learn to solve a lot of problems to develop high-level cognition. When you take a look at a problem, you naturally know the move to make. So that is by solving problems, by solving a lot of problems. Enjoy solving problems. And that's the only way you can move from being a learner to a master. All right. That's the only way to move from learner to master. Solve a lot of problems. So I have practice for you in this video. I have practice for you in this video, as you can see. So simplify. This is problem number 1. Simplify A, B, and C. So based on what you have learned in this video, you can handle this. Let's see the next. I still have practice for you. A lot of practice for you. Yeah. And this is another one. So P is giving us square root of 5 minus square root of 3. Find the value of P plus 1 over P. P minus 1 over P. Right? So find the values A and B in each of these expressions. So the left hand side equals the right hand side. Go ahead and find the value of A and find the value of B. Same this problem. And I have the answer keys. Yes, are you ready? The answer key is up next, so you can check your answer. Pause the video, solve these problems. Let me know in the comment section the ones you want me to throw more light on. So I'm flashing that. These are the answers. So very quickly. Now you can see my favorite quote: mastery and expertise are products of persistence and consistency in practice. I actually have a video narration of this quote on my channel, and I'm going to leave the link in the comment section. You can click on the link to study narration, video narration on this quote. Mastery and expertise are products of persistence and consistency in practice. You have to keep up the practice. Thank you for watching this video to the end. Please subscribe if you have not yet subscribed, and click on this notification bell so that you know when anytime I make a video, you're naturally alerted. All right. Follow me, Temple AK Academy, on YouTube, Facebook, Instagram, TikTok, chess.com, and LinkedIn. And of course, you can send a WhatsApp message. You can send a WhatsApp message. You can send that WhatsApp message. Yes, that's my WhatsApp. You can send a message. And you can also look out for a lot of my publications on Amazon. A lot of books I've written. You can purchase some of these books on Amazon. Just type Temple AK on Amazon and then follow me on Amazon by following the button. And then you can email if you want. TempleAKAcademy@gmail.com. Like, share, and comment. Let me know your comment. What you want me to use in videos. What challenging areas you have. So I'm your regular coach. My name is Temple AK, signing out for now. Thank you. Keep up the practice. Stay blessed. Remain solid.